Welcome back to a new video in our Wells Hydraulics course. So we're starting a new module on transient flow. So the first module was all on steady state configuration in confined and unconfined aquifers, and then we did a lecture on modeling and finite difference approximations of these equations. Here we are starting to look at the equations of motion with a transient state, meaning there's adjusting in time, if you will. So if we look at this general Boussinesq equation here on the top, you can see that on the right-hand side, we do have a time differential, and that's really where that transient issue arises, right? So not everything is constant, things are evolving in time. We use transient solutions usually to do aquifer tests because we don't want to wait, until everything is at steady state. That can take days or weeks or even years sometimes for a well to be at complete steady state. So typically what we do is we start the pumping at time zero, and then we measure drawdown over time. And you have an example here on the right-hand side of that kind of data where, of course, the head drops, so the water level drops in the well. And we can measure that drop over time and then say something about the aquifer, right? That's how we conduct an aquifer test. So again, things are not constant in time, but the head is dropping, so we're measuring this and trying to infer aquifer properties. So in a confined aquifer, right, we can calculate storativity and not only hydraulic conductivity. Remember in that last lecture, last module on steady state equation, we showed that we could calculate hydraulic conductivity, but not storativity. Here, because storativity is on the right-hand side of this equation, if we have the time variable, showing up, then now we can actually get to that S term that's here. Okay. All right, a few assumptions for a confined aquifer. Again, confined top and bottom. There's no recharge, so nothing is leaking into it. Everything is just the confined water itself. The aquifer is compressible, so remember that in confined aquifers, the water that we get by pumping comes from the compressibility of the water and of the skeleton itself, right? So again, the depth of the aquifer is constant, everything is constant, it's full of water, so the only thing that changes basically is pressure in there. And then of course the well is pumped at a constant rate, right? So there's a pump that just, pumps 1 cubic meters per minute or whatever, that may be. And again, that's sketched to remind you the configuration at the bottom. Also, when we talk about pumping tests, remember that the drawdown, right? So we can just swap signs and use drawdown instead of head. They're just equivalent, just the sign is flipped. And here we're introducing the well function. So you already saw it in that previous figure right here, right? So you can see the data is the dots here. That's the drawdown measured over time in a well. And you can see that we have aligned that data on a curve. This curve is called the well function. Okay, so the well function W of u, so u is an argument of that function, is plotted here at the bottom. So this is really important because we'll be using this over and over and over in these lectures in that whole second and third week, most of this course basically. Again, the well function is essentially the typical behavior, in this case of a confined aquifer, over time, right? So this is, you could see before, we could line up the data perfectly with that function, and that's exactly what they're for. So they're like type curves, if you will, for the behavior of a confined well over time. So again, the well itself, the well function, W of u, the y-axis, right, is equivalent to expected drawdown or normalized drawdown, if you will. And the x-axis here, the 1 over u, is a surrogate for time, right? It's the same as drawdown over time, except now it's a well function. Oops, excuse me. So you can see here, this is the solution, right? The drawdown equals q over 4 pi t wu. So if we know u, we can, the argument here, right? The argument of that function u is r squared s divided by 4 t, the transmissivity, and then time, okay? So once we know something about u, if we can get u, basically we can get the storativity, okay? So this is really what we'll be using, and we'll do an example in a minute. Also known as the Thies curve or Thies curve. Thies curve, this is just the curve, the typical unsteady well function for a confined aquifer, the Thies curve. This is our base case scenario. So here we have the process to use our type function, our Wells function. So of course, first you start by plotting your data, then you line up the data with the Wells function and find what we call a match point. So here, typically you want to choose a match point at 1 and 1. That's just easier to plug in those numbers, right? If WU is 1, then it's just 1 here and it's just easy. Also notice that the x-axis is actually 1 over u, not u. So again, if 1 over u is 1, then u is 1, and it's just easier to use u in here as 1. So again, try and pick the match point at 1, 1. Of course, once you have that match point here, you want to read your drawdown and your time in the data plot. So again, that match point was right about here, I believe. So you go down here in your data and you read your drawdown and your time. Finally, once you have time and drawdown and you have u and w of u, so again 1 and 1 here. Now we have time here and we have the drawdown here. Now we have everything. We can just plug in and find the transmissivity and the storativity for this particular aquifer. So this is really how the method works, and we'll do an example. We'll plug in those numbers in a second here. So in the next video, I will show you this example again. I will just run through the calculations to actually measure transmissivity and storativity for a confined aquifer, but this was a presentation of the general method, graphical method. Thank you very much.